In this video, we're looking at two examples of the linear programming problems. We're continuing what we did in the previous video. So this is just more examples to reinforce this method of corners procedure. In this example, we've got deluxe river cruises that are operating a fleet of river vessels. The fleet has two types of vessels, a type A vessel that has 60 deluxe cabins and 160 standard cabins, where there's also a type B vessel that has 80 deluxe cabins and 120 standard cabins. Under a charter agreement with Odyssey Travel Agency, Deluxe River Cruises is to provide Odyssey with a minimum of 360 deluxe and 680 standard cabins for their 15-day cruise in May. It costs $44,000 to operate a type A vessel and $54,000 to operate a type B vessel for that period. How many of each type vessel should be used to keep the operating cost to a minimum, and what is that minimum cost? Now notice here, when we're optimizing the objective function, we're wanting to minimize. We'll see the differences in this, which is the same procedure, but when we graph that feasible set, it will look slightly different. All right, so the first thing that we do is we find the objective function. The objective function in this case is the cost function. All right, so how much is this going to cost? Well, it costs $44,000 for a type A vessel. We'll call type A vessel X, and it costs $54,000 for a type B vessel. We'll call the type B vessel Y. Okay, so now once we have our objective function, we need to determine what our constraints are. So we're constrained by the number of deluxe and standard cabins, right? Because we want to have a minimum of 360 deluxe and 680 standard cabins. So we need to find what these inequalities are going to be for that. So for the deluxe, we need a minimum of 360. That's greater than or equal to 360. We can have 360 or more, but we cannot have less. And so we have 60 deluxe cabins on the type A vessel, 80 deluxe cabins on the type B vessel, right? So we could set that up as 60x plus the 80y, and that's got to be at least greater than or equal to 360. And for the standard cabins, we have 160 standard cabins for X, 120 standard cabins for Y, and that's got to be at least greater than or equal to 680. And of course, we have our typical constraints of X greater than or equal to 0, Y greater than or equal to 0, because we cannot have a negative number of deluxe and standard cabins. All right, so now we're ready to graph the inequalities and find the corner points of our feasible set, and then plug into the cost function, see which one gives us the smallest cost. Okay, so when we're graphing this, we know that our approach is to find the X and Y intercepts. Okay, the X-intercept is found by letting Y equal 0, which is equivalent to dividing the constant on the right-hand side by the coefficient of X on the left-hand side. So 360 divided by 60 is 6. That's the Y-intercept. We're going to find all the intercepts first, and then we're going to plot it on the graph. For the Y-intercept, we divide the 360 by the 80. And 360 divided by 80 is 4.5. Okay, now for the X and Y intercept of the second inequality, we're dividing the 680 by 60. 680 divided by 60 by 160, excuse me, 680 divided by 160 is, that looks better, 4.25, or 4 1/4. And then 680 divided by the 120 is 5.66. Let's write that as a mixed fraction there, just so I don't have to do any approximation, still getting that exact value. Okay, so let's graph this on our Cartesian coordinate plane. All right, so here is our 6, 0 here, and then the 0, 4.5, and we will draw a line through that. And which side are we going to shade? All right, so we can use our origin, right, which means that the left-hand side would become 0, right, since x is 0 and y is 0. And 0 is not greater than or equal to 360, so that's a false statement. So we will shade the side opposite of the origin. Okay, so now we'll do the same thing for the second inequality. We got 4.25, 0, and 0, 5 and 2/3, 5.66 repeating. And we'll draw a line through those 2 points. And again, we're saying that if we choose the test point 0, 0, we plug that in, the left-hand side becomes 0, and 0 is not greater than 680. So again, we'll shade on the side opposite of the origin. Okay, and so the solution set here is where you see the blue and the red overlap, which is everything above this region. All right, so we've got 3 corner points here, here, and here. And we know this point is the x-intercept 6, 0. We know this one is the 0, 5 and 2/3. We just need to find this point here. And since we're drawing this by hand, we should not look at the graph to try to determine what that point is. Let's use the elimination or the substitution method. In this case, I'm going to use the substitution method. Because these numbers are so are larger to where the elimination method may be a little more difficult to work with. So if I take this first equation and I solve for x, all right, so that would be 60x equals 360 minus 80y. And divide both sides by 60, that leaves me with x equals 6 minus 80 divided by 6. We'll simplify down to 4/3. Make sure that you're writing that as an exact fraction as opposed to writing it as an approximated decimal. All right, so now x equals 6 minus 4/3 y. I'm going to substitute that into the second inequality to get 160 times 6 minus 4/3 y plus 120y equals 680. All right, now simplifying here. 160 times 6 is 960 minus, let's see, 160 times 4/3 is 640 thirds. I'm going to leave it as that 640 thirds for now. Y plus 120y equals 680. Okay, now we can subtract the 960 from both sides and then combine the like terms of the y. So negative 640 thirds plus 120 gives us 280, negative 280 thirds y. And dividing both sides by this negative 280 thirds, that will leave us with y equal 3, right? Because the negative 280 are going to cancel when you divide. So y equals 3, and then we can substitute y equal 3 back into our x statement here, that x is 6 minus 4/3 y. That'll reduce down to 6 minus 4, which is 2. All right, so this point here is 2, comma 3. Okay, and there are other ways you can find that point. We use the substitution method here. You could use the elimination method. You could use the Gauss-Jordan elimination method. You could set this up as a matrix and work it that way. There's many methods you could use. As long as you can find that point, I don't care how you find it, as long as you find the correct one. All right, so now we've got 3 corners, right? And notice that this region is unbounded, right? It's unbounded because it keeps going up and to the right. There's no upper bound here, so that's referred to as an unbounded region. Okay, but anyway, we take our 3 corners, we plug it into our cost function. Okay, so we're taking 0, comma 5 and 2/3, and for the purpose of substituting in, maybe I should write this as 17/3 just to make it easier to substitute in 17/3, and I'll plug that into the cost function. 44,000 times 0 plus 54,000 times 17/3. 54,000 times 17/3 is 306,000. Do the same thing with the 2, comma 3. 44,000 times 2 plus 54,000 times 3. Which is 250,000. And then finally the 6, comma 0. 44,000 6 plus 54,000 times a 0 is 264,000. Okay, so now our final answer is the smallest of these values, which is 250,000. Okay, so how many of each type vessel should be used? Right, we should use 2 type A vessels, 3 type B vessels, which would give us the minimum cost of $250,000. Okay. All right, so let's take a look at one more example with the method of corners. And while we're making that transition, I'll say that the method of corners works very well when you're only in 2 variables. But when you get to 3 variables, that's where the problems come in that makes the method of corners not work so well. And especially if you get more than 3 variables, it becomes impossible. So the next section, next week's lesson, will cover another type of method, which is referred to as a simplex method, which overcomes the obstacle of having more than 2 variables. Okay, but let's take a look at this one. We got the Madison Finance that has a total of $20 million earmarked for homeowner loans and auto loans. On the average, homeowner loans have a 10% annual rate of return, whereas auto loans yield a 12% annual rate of return. And management has also stipulated that the total amount of homeowner loans should be greater than or equal to 4 times the total amount of auto loans. And we want to determine the total amount of loans of each type that Madison should extend to each category to maximize its return. And what are the optimal returns? All right, so the first step is we want to determine what our objective function is, right? What are we trying to optimize, right? We're trying to optimize our returns. So and we're going to just write this as a profit, right? We're doing returns. That's how much profit that we're making off of our investments. Okay, so what's our profit function, right? Our profit function is that we're making 10% on the homeowner loans and 12% off the auto loans, right? Where we're calling X the homeowner loans and Y the number of auto loans. That's what we're trying to to optimize, maximize in this case. All right, so we need to know what our constraints are. Okay, so we have $20 million that we can use for these homeowner loans and auto loans. Okay, so we cannot use more than $20 million, right? So that's our first constraint, is that if we add the amount of home loans plus the amount of auto loans, that cannot be more than $20 million. Okay. Now we're going to need two restrictions, at least two restrictions. Right? So that's the first one, is the total amount of money. Okay. Our second restriction is going to come from the management, right? We're stipulating that the total amount of homeowner loans should be, okay, so the total amount of homeowner loans, right? So that's X, should be greater than or equal to 4 times the total amount of auto loans. Okay. And of course, we still have the restriction that X and Y must be greater than or equal to 0. Okay, now let's rewrite this statement here, X greater than or equal to 4Y, just to make it look like, you know, the first inequality. We'll subtract 4Y from both sides. X minus 4Y is greater than or equal to 0. Okay, so now we'll graph these two. All right, so we can first graph the inequality X plus Y less than or equal to 20 million. All right, so if you find the X-intercept, that means Y equals 0, so X is equal to 20 million. Same thing for Y. If you let X equal 0, Y is going to equal 20 million. So you've got 20 million for both the X and Y intercept. And so let's count by 5 millions here, right? 5 million, 10 million, 15 million, and that gives us up to 20 million. All right, so we got this point here. Same thing on the x-axis. Right, there's our x-intercept. We'll draw a line through these 2 points. Okay, then we'll do the same thing for the second inequality. For this one, this may be an exception here as far as finding the X and Y intercepts, because if you let Y equal 0, of course you get X equals 0. And if you let X equal 0, then you also get Y equals 0. It only gives you this one intercept at 0, 0, right? It's crossing the origin. So maybe it's best to put this in slope-intercept form so you can get an intuitive understanding of the behavior of this graph. All right, so subtract X from both sides, you get negative 4Y greater than or equal to negative X. And then divide both sides by negative 4, you get Y less than or equal to. Remember, when you divide by a negative, the inequality sign flips. And you divide by 4, so that's 1/4 X. All right, so the slope is 1/4. So as the Y increases by 1, X increases by 4. So up 1 to the right 4 units. You know, these are in units of a million. That's fine. We're still going up 1 and over 4, and we can draw a line through these 2 points here. Okay, now I didn't do my shading. Let's go back and do that. For my red line, right, I can use my origin for this first inequality anyway. If I choose my test point to be the origin, then my left-hand side is 0, and 0 is less than or equal to 20 million, so we'll shade on the same side as the origin. And then we'll do the same thing. Well, not the same thing here, because we cannot use the origin since the origin is on the blue line. So we have to choose some other point. Okay, some other a convenient point, maybe 0, you use 0, 1. I mean, that would be good enough, right? That'd be good enough. That would not be on the line, and it would be, this point here, 0, 1, something that's on this side of the line. And you would substitute in, right? I'm going to use this y less than or equal to 1/4 x. So if y is 1, x is 0, is 1 less than 0? No, it's not. 1 is not less than 0. So we'll shade on the side opposite of that test point. So we'll shade this region here. So now our feasible set is this triangle that we've got. We need to find the corners. And I know this corner is 0, 0, which of course is not going to maximize anything. I've got this point here, which is 20 million, 0. I just need to find this corner right here, which is the intersection of my two inequalities. And I can, since I have x greater than or equal to 4y, I can use that as my substitution into my first inequality, x plus y equal 20 million, replacing the x with the 4y, so that's 4y plus y equal 20 million. And solve for y. 20 million divided by 5 is 4 million. So when y is equal to 4 million, x would be equal to 16 million. All right, so this would be 16 million, 4 million. All right, so now we take our 3 points, plug them into the profit function, the objective function. Actually 0, 0, not much reason to do that. We know that would give us a profit of 0. So let's just focus on these two right here. Okay, so the profit, 0.1 times, let's use the 16 million first, plus the 0.12, 4 million. Okay, so we've got I'm going to write this out, 1.6 million plus 480,000 that gives a total profit of $2,080,000 for the 16 million, 4 million setup. Now we'll do the same thing for this 20 million, and we've got 0.10 times 20 million plus 0.12 times 0. That gives us 0.1 times 20 million, that's 2 million. Okay, so the maximum profit is the 2,080,000. That's going to win. So how should we divide the money into the categories? We should have $16 million in the homeowner loans and 4 million designated for the auto loans. That would give us a total return on investment of $2,080,000.